Oh my. Okay. Come on. Let's get started. It's exam review day. Um, so, uh, a couple quick housekeeping items. I say here homework up to 2.7 is graded, but I need to check and see if those are posted. So the new Blackboard, there's actually kind of a nice feature where the way it works is you can grade them and then post them all at once, and that it didn't really work like that on the old Blackboard shell. But so I think the homework up to 2.7 is graded, but it might not be posted. I need to check on that. So 2.8 I know is being graded, but the solutions and everything up through the exam are now available. And we're going to be talking about exam one. So just to remind everybody, exam one's worth 20%. I put that on my exam review slides. The second exam, this isn't a typo, the second exam is only worth 15% because it only covers bolts and welds. And you're going to see that for a senior level engineering course, bolts and welds are pretty easy. Like they're pretty straightforward. So with that, today what we're going to do is discuss the first exam. And really what I'm focused on is just making sure you understand the format, making sure that you understand what's going to be on it. I will mention before we get into the review, I don't know that I formalized it, but if you have not yet started to tab your manual, what I have placed are, I really only have two tabs placed in the body of the manual, and one of them is for this page right here for FY and FU for the yield stress and the ultimate tensile stress, and the other is shear lag. That's the only thing I have within the manual bookmarked. Okay, that's the only thing I have. Now, other than the shapes. Now, the shapes, I have a tab for W shapes, for C shapes, for L shapes, and for WTs. That's what I tab. I mean, we might use more. I mean, it's possible that we have like MCs or HSS or what have you. All that's possible, but I think like by and large, this is probably the most common. If there was a fifth tab, I would probably add HSS, but we really don't mess with that a lot in the class. I mean, it's not like it's any different. We can, but I just wanted to make sure that you all knew what I had bookmarked. Okay, so let's talk about the logistics. So first off, the exam is going to be, so you all had me for class before, so there's nothing like, all that surprising on here. I'm going to have 4 to 5 short answer, like conceptual type questions. And when I say short answer, I mean like no more than 1 to 2 sentences. I went back to as you all have had me for class before, what I usually do after an exam is I come up with some bullet points for like, here's some suggestions for what to do on the next exam. And when I looked at my bullet points for when I gave exam one last year, like one of my first pieces of advice was to try and be more succinct in your conceptual answers, because you've got 55 minutes, right? And you're spending, writing, an essay on a problem that's only worth 3 points. So, be cognizant of time limits and whatnot. But to be clear, the exam is not intended to be time critical. Like, I take the test myself, and I can do it. If I can do it in 20 minutes, you can do it in 60 minutes. That's my rule of 3 that I've used for a long time, and that applies to this test as well. It is open book and closed notes, and so by open book, I mean you got to have the manual. So just right off the bat, don't forget it. Don't forget your manual. You're going to need it, okay? Don't forget your manual. I am going to allow you a formula sheet, okay? And I'm going to talk about that here in a bit. I say a straight edge might help. I don't know. That's probably hit or miss. I usually always tell students to bring a straight edge on my exams. I tend to think it's not a bad idea. It might not be the biggest deal on this exam, but you all know by now that you're drawing schematics of connections and whatnot. So having a straight edge might be kind of nice. In terms of the formula sheet, I really am okay with whatever you put on it. The one thing I ask that you don't put on it is like a fully worked out example problem, and really that is for your benefit more than it is for mine. It's really easy to do to put a problem on your formula sheet and use 3/4 inch diameter bolts, and then I put a problem on the exam that uses 7/8 inch diameter bolts, and you accidentally pull the value from your formula sheet onto the exam, and suddenly the problem doesn't make any sense anymore because you're pulling in values from your formula sheet on the exam, getting everything mixed up. So I'm okay with a little bit snippets here and there. The only other rule, which I've mentioned this before, so this isn't like a big surprise in some of my other classes, but I do want the formula sheet to be made by you, okay? And what I mean by that is I am perfectly okay if you snap an image here and there out of the slides, but what I don't want you to do is take a bunch of slides, put them on an 8.5 by 11 and hit print, because the point is I'm sort of forcing you to study a little bit. By actually organizing your thoughts and putting them on a formula sheet and making the formula sheet yourself, when you come take the exam, you'd be surprised how little you're going to look at it because it's in your head, because you made it, okay? So I don't care if it's word processed, I don't care if it's handwritten, I don't care about any of that, but make the formula sheet yourself. That's what I would strongly suggest, okay? Okay, let's talk about the topics on the exam. So what I'm actually going to exam you on. So it's going to cover two things. The fundamental stuff that we did at the very beginning of the semester, but really the star of the show is tension members. That's the really what we're going to be talking about here. So for the fundamentals, make sure that you can generally describe like what's going on with structural engineering. I'm not going to get too fancy with some of these questions, but just make sure that you're aware of it. And I want you to understand the difference between allowable stress design or allowable strength design and LRFD, load and resistance factor design. But tension members, that's the star of the show. So I want you to be able to analyze tension members according to gross section yielding, net section fracture, block shear rupture, and be able to assess slenderness limitations. And I want you to be able to design either an economical plate or an economical rolled section for a prescribed loading. And when I say economical, I mean lightest weight, okay? I also want you to be able to select economical threaded rods for prescribed loading. But I mean, that one slide, that's the exam. I mean, but that's also everything we've been talking about for the past, few weeks. Everything else that is in this slideshow is the greatest hits from the past, 10, 12, or 12 lectures. So I just sort of snipped out the slides that I thought were the most important. So first off, LRFD, just the basis of LRFD in general. The idea that when we're looking at strength limit states, we compare factored resistances and factored loads. Our factored loads come from our statistically calibrated load combinations, and our factored resistances come from the spec, where we compute nominal resistances and then adjust them by a resistance factor. Our LRFD load combos, there's all 7 of them, but really, as long as you know how to operate the first 2, that's going to get you through most of the design that you need to do. Those are the ones that are most frequent. Tension member limit states, so we have gross section yielding and net section fracture, and I say we're going to add a limit state called block shear. Now we've added it, so we know what that's like. We know that we can get properties of steel from table 2-4. Again, this screen capture doesn't match what's exactly in the manual because it's from one spec prior. They haven't released a digital edition of 16th yet, so some of my pictures might still go off the 15th, but you've got that with you. The complete expression for net area, so it took us a little while to sort of derive this, I guess you could say, but we now have a complete expression for net area. And I would say this slide applies to really any member because we have for bolted connections that it is the gross area minus the sum of all the bolt holes, which is the hole diameter plus or the hole diameter times the thickness, and then but we add any necessary stagger factor. So you have plus the sum of all s squared t over 4g terms, and that's if there's any stagger patterns present. And that's for bolted connections. If you have a welded connection, the net area equals the gross area because you're not removing any material to facilitate the connection. Shear lag, now this one actually does come from the new manual because that comes from the spec. Shear lag factors, so remember you have multiple cases that can apply. At a minimum, you should be asking whether or not you're in case 1 or case 2 because it's always going to be one of those. It's either all the elements or some of the elements if you're dealing with a bolted connection. If you're dealing with a welded connection, you know you're going to be in some of these later ones, what have you. The step-by-step process for design. So in design land, we're still going to consider yielding and fracture as our two strength limit states for design. So one question that comes up is, do you need to design for block shear? Well, I mean, yeah, you do need to design for block shear, but you certainly don't try and select a member and try and configure that monstrosity of an equation inside this. Typically, the way block shear is handled is you select a member based off gross section yielding and net section fracture, and then you just check block shear later. So you're not going to fit block shear into all of this. So the design process is going to be the same with or without block shear. So you're going to determine the factored load. You're going to compute your two design parameters, your gross area for design and your radius of gyration for design. And then based on these two, pick the lightest shape available within the constraints of the problem that has at least these properties. And then once you have these, you have to analyze the shape in order to verify its performance. And then when it's all said and done, try and compute an efficiency. Here's block shear. One question that I notoriously get, and I'm going to go ahead and answer it right now. Dr. Mike, are we going to have to do a block shear problem for a staggered connection? No, you are not going to have to do that. Okay? It is really not any more difficult because if you had a net area in tension that was staggered, you just put a stagger factor on there. So it really wouldn't be that different, but we're not going to worry about that. So don't worry. No stagger, no block shear for staggered connections. Here is our expression for Rn. We have our gross area and tension, net area and tension, gross area and shear, net area and shear. The big thing that I have noticed in exams prior is do not forget the 0.75 resistance factor for block shear. It's really easy to go through all this hullabaloo to compute the block shear capacity and then forget the 0.75. So don't forget that. For threaded rods, here's our expression, you know, the 8/3 times the square root of PU divided by FU pi. And really all that's coming from is just saying that the resistance factor is 0.75. The stress is 0.75 FU, so there's 2 3/4 or 6/8. And then we're going to, couldn't help it. I couldn't help it. You missed it. I said, so you've got 2 3/4 terms or 6/8.
Yeah.
Okay. Y'all missed that before class. Okay. So we have 2 3/4 terms, and then there's the bolt, or the area of the bolt, which is pi over 4 d squared. So we have a 3/4, a 3/4, and a pi over 4. So that's where this 9 pi over 64 comes from. And just rearrange and solve for the bolt diameter, and we get this. So design of a threaded rod is quite easy. Probably the hardest part on a threaded rod problem is the load, which I will go ahead and tell you. One question I get asked, and so this is going to be my way of answering it. Like, what is the structural analysis demands on this exam? What I will tell you is this is a structural steel design exam. This is not a structural analysis exam. That's going to be my answer. Does that make sense? So I'm interested in your ability to design, to do steel design, not structural analysis. That was last semester. Okay? That, ladies and gentlemen, is what I have for the review that I've already prepared in advance. But now it's your turn. So floor is yours for any questions that you have, anything you'd like to discuss, any topics that you want to review. Floor is yours. Yes?
Could you go over like a staggered path problem?
Could I go over a stagger path problem?
Yeah.
I could. So
I'm just confused on how to find like all of the paths.
Sure. Come on. I gotta take my keyboard off. Okay, so what I'll say here, here's what I'll do. I'll draw sort of a sample connection, and then we'll start identifying some paths. Okay, so I'll just make one up. Okay, so first off, let's draw a plate. And let's do this. So what I mean is, here's the plate and I'm yanking on it. So I'll start putting in some bolts here, and I'm going to come up with sort of a weird pattern. Okay, if that makes any sense. I'm going to come up with something that's kind of weird. Okay. How do I want to do this? Okay. Okay. That's weird. I know. That nobody would do this in the real world, right? But I'm picking something that's kind of strange because I want to make sure that we can conceptualize what we're doing. Okay. So the first thing I'll do is I'm gonna do this, and my main reason for putting this little grid here is just so that we're all clear on like which ones are the diagonal paths and which ones aren't. If that makes any sense, right? So we know that like that's going to be diagonal and that's not. That's just for our vision sake and whatnot. And let me see if I can make this a little neater. So we'll do that. Okay. All right. So this is me doing it live. So okay. All right. So the first question to ask when we're identifying net paths is which is going to be the lead line? Is it going to be the bolts over here, or is it going to be the bolts like over here, the left or the right? Everything over here. Because remember, the idea is if you're standing and looking this way, then this is the lead line. So what I'm going to do is I'm going to, how do I want to do this? Let's do this. Let's color in the bolts that are going to be lead line. Okay, these are the lead line bolts. Okay, so the first question I would ask you, just like, let's not letter anything, let's not do that, is this a viable path? No, because this is not like, if I cut, like imagine this plate is a sheet of paper, and I take a pair of scissors and I cut along that red line. The paper is still pinned down by these two, right? So this is not a viable path. Everybody with me so far? Okay. All right. So, okay. So what I'm going to do is I'm going to start naming the paths and whatnot. Now the way I'm going to handle this, I'm just going to call the top of the plate A, like anything on the top of the plot or top of the plate is A. We'll call this B, C, D, E, F, and anything down here is G. Okay? So, and let's also, for the sake of discussion, say that all these increments are 3 inches. And I'm just saying that because I let's just say that like all these diagonal paths, like they're all the same. Okay, I don't want to try and make that part confusing. Okay, so let's see if we can start identifying some paths. Okay, and you pick one. You started this. You pick one. Let's start out with the easiest one, the one with no stagger. ADFG. So we're just talking about boom. And is that a viable path? Yes, it's a viable path because I could cut this and I can take that piece of paper off, right? I can take that off. Okay? So that's a viable path. Okay? So we're going to call this ADFG. And what I'm going to do is I'm going to say that that's going to be the gross area minus 2 holes. Is that fair? Okay. All right. So somebody give me another path. Somebody else. Okay, A, B, C, D, E, F, G. All right, so and there you go. And so that you're aware of my rule, whenever I go from like this end down or what have you, or if I go like from D up or C or B, it's just going to go up. Path of least resistance. Is that a viable path? Yes. Okay, so if I look at, you know, so that is the gross area minus how many holes? Now, how many stagger factors? 4, right? So 1, 2, 3, 4. Okay. All right. Let's see. I'm not done. I want to find a couple more. Are there any other viable paths? Okay, hold on. So you said A, D, E, F, G. And which one? A, C, D, E, F, G. Right? That's one. Okay. How about this one? How about that? That's a viable path. Isn't it? It's going to fully separate the member. Like, I don't understand how that's not a viable path, but this is. You see what I mean? Here, okay, so here's one. Here's one. See what I mean? Those are viable paths, right? Like 3 years from now, I'm going to use this as an exam problem. You can, so 3 years from now, when their students are, what the heck was that, Dr. Michelson? Say, I'm giving you Mr. Elsie's email. You're going to have to reach out to him. It's all his fault. Does that make sense? Okay, did that answer your question? So the idea is, first off, which is the lead line? And then the second is, what are the different ways I could pass the pair of scissors through the plate such that I would completely tear off that other plate on the other end? And once you have that, it's just the number of bolt holes and the number of diagonal paths. Now the big thing is, let's just use this path as an example. How many stagger factors for that path? 1 or 2? 2. You do not treat this as one big old stagger factor with an S of 6 and a G of 6. You don't do that. You do 2 different stagger factors of 3 apiece, because the expression is S squared T over 4G. It doesn't work mathematically to just combine it. You don't get the same answer. Okay? Does that make sense? Because you can't say like 6 squared over 4 times 6 and say that equals 2 times 3 squared over 4 times 3. It doesn't work like that. Okay, so you have you can't do that. Okay, does that make sense? All right, any questions on that? Everybody good?
Is it safe to assume that like the line with the most diagonals is like the?
That's a great question. So I'll answer you 2 different ways. Okay, for a problem like this, you can start to identify a bunch of different failure paths, right? Now, because all of the dimensions are the same, you're going to start to notice a pattern, okay? And you'll start to notice real quick whether or not it's the path with the least number of holes and no stagger, or the path with the most number of holes and all the stagger. Like, you'll notice it pretty quick. The other thing I would mention is that it's easy to do that on this problem when all the stagger factors are going to be the same. When you start having angles, remember when we took the angle and we turned it into a plate and you had different stagger factors on either end? That's a little more difficult, okay? You kind of have to just roll up your sleeves and do it, okay? But what I'll say is usually on problems like that, there are less paths to check. So it's not like you're having to like, it's not like you're having to check 6 or 7 paths and they're all independently, unique and different. Like that's not going to happen. Does that make sense? But yeah, so like on this problem, what I can tell you is like, I would check this one and check this one and maybe check a couple others, and after a while I'm going to start to see a pattern. And even I might not check all of them because I'll go, okay, I kind of see it's probably this one, Because here's the thing, if the stagger factor is bigger than the whole area, then it's not going to govern. See what I mean? Or proportionally bigger, if that makes sense, because it's 5 holes and 4 stagger factors, so. It's a better way of saying it. Sound good? That's a good question, by the way. What about it? Come on, there's got to be some more questions. Can make me work for a living. Sure.
Could we look at like, kind of like along the same lines, like figuring out the pathway for like the block shear?
Sure. Okay. So. So I'll say a couple things about block shear, okay? How do I want to do this? Okay, here's what we'll do. Okay, hold on. So what I'm going to do is I'm going to cheat a little bit. Okay. So I've got the same connection over and over again. And what I'm going to do is I'm going to define a couple of different paths, okay? Now, first off, to be clear, the rule for block shear is that you have to create a path that surrounds all of the bolts, does the same thing that the stagger paths does in the fact that if I take a pair of scissors and cut around that, I'm totally separating the member. But it's got to include a shear path, okay? So what I mean by that is, and bear with me, is I could have a path that looks like this, and I rip out this chunk, like that's an option. I could do a path like this, like that's an option. But this is not an option, okay? The reason why this is not an option is because this edge and this edge is not subjected to shear. See, if I fail this way, this isn't a block shear failure. This is just a net section fracture failure. I'm just snapping the member in half. So there's no block shear phenomenon going here. So this is the one that is not a viable option, okay? Now, so I'm going to draw a couple of different options for block shear failure paths. Okay, I'm going to draw a couple of different options that meet the rules, but then we're really going to clearly see why only one makes sense. Okay, so let me draw an option. Okay, so one option is this. So this, and this. Now, why did I use different colors? Why did I use red and green? Shear versus tension, exactly right. So I propose that this is a potential block shear failure path. Okay, that I could rip that out. I say it's a potential block shear failure path. I don't think it's the right one. Okay, now why don't I think it's the right one? The reason I don't think it's the right one is because I think this one's the right one. Okay, let me move this up a little bit. I think that this is the right one. Now, first off, can anybody tell me why I would think that this is more likely to happen than this?
The shortest path.
It's the shortest path, okay? So think about it like this. Those red lines and green lines, going back to my scissors analogy, that's the amount that I have to cut through this connection in order to separate, right? It's a little easier on the scissors to cut this path than it is this one, would we all agree? But let's also make sure that we're following that technically. So this second option is going to result in a lower AGV. Like the AGV for this path is half as much as it is for this one, right? Granted, we're getting a little bit more AGT, right? This one's a little bit shorter than that. But on the whole, that's a lot less area. If the area goes down, what happens to the capacity? Capacity goes down, right? If the capacity goes down, so that means I'm going to have a capacity for this and a capacity for this, and which is going to govern, which is going to be my conservative option, the one with the lower one, right? So that's why I'm saying that between this and this is the one I'm going to go with, because if I go to the hydraulic press channel on YouTube and I put this, on, well, it'd have to be going the opposite way. It'd have to be yanking on it, not pushing it. But if I take this and I yank it, I'm going to fail this way first than I am this. Okay. Now, I don't think I fully answered your question because I didn't talk about like identifying paths. So what I'm saying for path identification is you've got to configure it such a way that it leaves all the bolts intact and it completely separates the member. So I'll throw one out there that's kind of bizarre. Here's an option. Like, it's a weird one. But it would work. Because I could take my pair of scissors and cut through the plate like this, and I could separate that plate from the board, but not cut through the bolts. Okay? So let's think about my rules here. It includes a shear path. It completely separates the member, and I don't have to snip through a bolt. This would be a viable path, but is this going to govern my capacity? Oh, of course not. No way is this going to govern, right? It just doesn't make sense, right? There's just way too much area to cut through, okay? So between this case and that case, it's not going to matter, okay? And like I said, I mean, you can get kind of bizarre with this. I mean, like you could say, okay, let's do this. You could do this. I mean, that's better, That's a little bit more realistic. But still, it's not... Oh, I accidentally... I don't think I meant to do that. Oh. Okay, I'm not redoing it. That's too much work. It's just going to be red. This is an option, and it's better than this, but again, this is more area, more scissor cuts than just this one right here. Does that make sense? Like, definitely that governs. Definitely governs. Did I answer your question? Okay. How about everybody else? Is that good? Yes.
So for this type, I know on homework 2.8.
Yes.
With the W shape, like how does that change kind of what our cuts would look like?
So here's what's going on homework 2.8. Okay. The best way of explaining homework 2.8 is to look at this from a cross-section perspective. Okay. And so let me ask it this way. Okay, so hold on. man, I'm really trying to be accurate with this because it will help make the point. That's about the best you're going to get, but I think that's good enough. Okay, so what I want to do is I want to recognize that here's our bolts, right? Okay, so there's our bolts, right? Okay, but let's think of this also. Let's also recognize the three-dimensionality of it as well, right? So what I was saying is that the more viable option, like what I was saying on the solution, is that the viable option was to rip out these little chunks, right? And there were 4 of them on each end, right? This is what I was saying, okay? Well, my question to you is to look at this from a tension standpoint, to look at this from a cross-section standpoint. My question for you is it easier to rip through this tension area than it is the inverse of that? Which is the bigger area GT, area NT, the areas of GT, areas of NT? Is it this bit, this bit, this bit, and this bit added together, or is it ripping through the middle? Okay? What I'm saying is that there are 2 possibilities. The first possibility is essentially what I was suggesting, which is that we're just going to have 4 of these little chunks rip out, okay? The other option is that what we've got is we've got to rip all this inside stuff out. All this has to rip out, okay? And I think this is far less likely than this. Does that make sense? So that's why if you look at my solution for that, see, here's my solution. And what I'm saying is happening is that it's just those little bits ripping out, because it's either these 4 orange bits or it's all this middle, okay? And I propose that the middle would result in the same AGV and ANV, because it'd still be the same shear pass, but you'd have a whole lot bigger AGT and ANT. That's what I'm saying. Does that make sense? So yeah, this one, I knew this one was going to be a challenge. I knew that, so. Did that answer your question? I know you said you didn't get the answer. I'm still on the clock, so if you've got any more questions, this is the time. So. I'm having to earn my paycheck today. I like it. What's that? You go ahead and do it.
If we were, so if we have to design a member in the exam, do we need to do all 3 then, like block shear rupture as well?
So it'll tell you. What I'll tell you. So there might be a problem that says neglect slenderness or neglect block shear or whatever. It'll tell you. I'm not going to make that vague. I won't do that. Some problem, like you might have a problem that says do all 3.
Yeah.
You might have a problem that says just do this. But for everybody, read the problem. Because what you don't want to do is spend 10 minutes doing a block shear check and find out you didn't need to do it. Okay, don't do that. All right. So.
What was this, like the tributary area? Is that just like?
So that's what I was meaning when I was saying I'm going to be light on the structural analysis. So. What I will say is this. Of the 3 problems, some are more challenging than others, but the ones that I think are more straightforward are worth more. Okay? That's what I'll say on that. And I will say that while there are some challenges, I think it's also fair to say that they're all fair game. In other words, a couple years ago, I had a problem which I had fun with, and I had a pipe that was filled with mercury. And mercury has a specific gravity of 10 point whatever, right? And there were U-shaped threaded rods that were spaced every, 20 feet. And you had to use tributary area and fluids and specific gravity to figure out how much load was on the rod. I didn't do that this time. I didn't do that. As I mentioned, this test is really light on the structural analysis requirements. This is a steel design test. So this isn't a 312 test all over again. That's my answer to that. Any other questions? Folks in the back, how are we doing? Mow engineering is good. What we're gonna go with now. It's this fall. All right. Last call. Any questions? Going once? Going twice? One quick housekeeping. I am going to provide both the exam and like the scratch paper as well, so you don't need that. So you'll have scratch paper to work on. So I think you could probably do most of the exam on the exam, but in case you need any more paper, you've got some paper for that. Don't forget your manual. Don't forget your calculator. Don't forget a straight edge if you want it. Your formula sheet. Obviously a pencil. I will see you all on Friday. You got 8 minutes back.